The Canadian Galactic Plane Survey ran on the synthesis telescope here for 12 years. And the most important thing it produced was 11 PhD theses and 17 MSc theses. And some of our brilliant students are in this room. Tyler Foster in the back, almost back row there. Joanne Brown, unfortunately, had to leave at lunchtime. Both of those are on faculty in Canadian universities. Postdocs, perhaps first among them in all kinds of ways is Sean Doherty in the backyard, now in the back row there, now our boss. Roland Cotes, Gerald on the staff of Hertzberg in Victoria. I'm not even going to attempt a full list, and I won't mention the people who on the DRAO staff who were in the room who contributed. It was a big team effort. Now to the second part of the punchline here. When we started this survey, they told us that a survey is what you do with a telescope when it's no longer good for anything else. This was in 1995. It was kind of reviews we were getting. Well, the other day I picked up this volume from a science conference in 2004 and opened it at random. I read, "Surveys are indeed the currently favoured means to progress in astrophysics." I close my case. We are building the square kilometre array as a survey telescope. We are building survey telescopes. Surveys are the way to the future, and I think the Canadian Galactic Plane Survey had a lot to do with generating the credibility for surveys. Now, what was it about this telescope which made it such a good thing for surveys? And this is to the credit of its designers, Rob Roger and Carmen Costain, that it's ideal for imaging extended structure. The dishes are small. They had to be small. They came off a junk heap. We didn't have much control of that. The dishes were small, but that allowed short baselines. But the telescope was designed for complete sampling of the UV plane. It was very significant. And here's an example. This is one of those sources from the Vermilion River Observatory. If you take an image straight from the telescope, you can already do astronomy with it. Here it is after all the cleaning and self-cal and elegant deconvolution algorithms. But remember that this telescope was designed before clean was invented. And that's true of the VLA as well, and that's true of Westerbork. Clean was invented in about 1974, I think. And when it comes to H1, atomic hydrogen, for which this telescope was built, atomic hydrogen has structures on all scales, from big to tiny. And clean is a way of taking sparse data and interpolating in between. But if the sky's like that, you can't go inventing data with algorithms. You have to sample it. So the other important thing that we invented here was a way of adding single antenna data to synthesis telescope data. Of course, synthesis telescope data, you can have all the short baselines you like, but at some point the dishes are going to collide, and that's dangerous to your health. So you have to incorporate data from single antennas. And this was something that Lloyd Higgs did in an observation we made in the late 70s. Of course, at first, nobody would believe that the hydrogen had any structure in it. This is an early image of a field in Cygnus X. It's not a very good picture. You can't read the contours, or it's rather fuzzy. But I went to Westerbork, or to Leiden in 1977 and gave a talk on what we were doing at this observatory. And nobody would believe me that with interferometers, with an interferometric telescope, we were seeing anything in galactic H1. They thought that all we would detect was the absorption of point sources. Well, they were wrong. The H1 has all sorts of structures in it. So very early on, well, not so early on, by the 80s, we forged an alliance with the Max Planck Institute in Bonn, in particular with Wolfgang Reich. It's a collaboration that continues to this day. We just hope that the man doesn't retire. It has been very valuable in the high-quality imaging we do. Now, the ideas that defined the Galactic Plane Survey were that the interstellar medium has many constituents. And to understand what's going on in the interstellar medium, you have to look at one of them. You have to look at them all, because they all interact. There's this crazy interplay of the atomic gas and the molecular gas, and the dust has roles in there. But there's a relativistic component which turns up a synchrotron emission, and there are magnetic fields. And this came out of all the experience of the users of our synthesis telescope and from us, among those users. The other thing we needed was spatial dynamic range, which is a fancy way of saying big images with good angular resolution. And as we wanted to put this into a picture, so the idea that stars emit radiation and they ionize things and the stellar winds, so the combination of the return of radiation and material to the interstellar medium through stellar winds and supernova remnants affect the diffuse medium, and the diffuse medium then goes on to cool, forms molecular clouds and stars, and there's a whole very complicated galactic ecology, as we called it. Where did those ideas come from? Well, I've already said this, but within DRAO and the users of the telescope, but there was a very important meeting at the observatory here with the 5 colleges radio astronomy group in, I believe, 1992. Somebody might correct me there. And they were doing systematic mapping of CO in the galactic plane. But also, we had a very good reception to the papers we were publishing through the 80s. Now, we dared to dream of mapping the entire Milky Way. I want to make an important point here. I get a lot of credit for being one of the initiators of the Canadian Galactic Plane Survey, and that is not correct. It was Peter Dewdney, Peter Martin from University of Toronto, and Russ Taylor from Calgary who formed the first team, but I became the director in 1994, and it was my job to run the thing. A pilot project from the University of Calgary was an important step too. We'll get to that in a moment. There was an earlier proposal in 1987, after we'd completed the 408 megahertz channel, to map the galactic plane at 408 megahertz. Never really went anywhere. But the proposal for pilot fields came at the beginning of '93. In October '94, we had a consortium together, applied to NSERC. We discussed in Toronto what to do about it, but then we were turned down by NSERC, and somewhat to our surprise, NRC agreed to go ahead anyway. And we started in the spring of 1995 and kept going till 2007. It was very significant. A very significant event in this was this pilot project, which ended up in a paper in Nature. It had long been supposed that that particles, their energy and radiation gets into the halo through some kind of channels through the galactic disk, driven by stars in the disk. And here, here's the H2 region W4, and its exciting stars sit here. And to the bottom, it's blown a bubble in the interstellar medium, but to the top, blown a hole in the disk. The top is the atomic hydrogen, and there were clouds of molecular gas still in there, and this particular cloud, 2 rabbit's ears being pulled off there by the stellar winds. I knew I'd run out of time. Thanks, Tim. So back to the timeline. We were turned down by NSERC. We never really knew why. What they told us was that the users of the telescope, the people who were applying, had NSERC grants already, and they ought to have enough money to do that anyhow. But we suspect that there was some sort of NSERC-NRC rivalry in there. And 1995 was an interesting year. Some of the early speakers have been blaming various Canadian governments for things. Another government, which shall remain nameless, cut heavily into all kinds of government spending, including NRC, and DREO was supposed to close on the 31st of March 1998, and we were given a kind of 3-year sentence. But then we applied to NSERC again and finally ended up with a 5-year grant for the CGPS to the university community. And it looked a bit embarrassing that NRC was going to close this place halfway through a 5-year project. So by Christmas 1995, we got a stay of execution. 1997, the long-range plan for astronomy came out, and the Galactic Plane Survey was in there. Anyway, we got a good Christmas present in 1997, and we're still here. The very first paper out of the Galactic Plane Survey was written by Gerald, in the back row there, again showing clumps of molecular gas being torn apart by the radiation from a stellar wind, and from stellar winds, a very powerful young star, and tails of atomic gas coming off there, the dynamic interstellar medium. Now we've got to hurry ahead and just look at the major results. Well, the most significant thing that a scientist can do in praise of another scientist is imitate what's going on. So pretty soon there was a Southern Galactic Plane Survey and a VLA Galactic Plane Survey. Rotation measures using this polarimetry channel that Dave was talking about, rotation measures through the Galactic Plane Survey. This is before the CGPS, and from Joanne Brown's work, this is after the CGPS. And to this day, this telescope is still producing more rotation measures per square degree than any other telescope, but is shortly to be overtaken, I think, by a new generation. And that has led to this picture from Joanne of the magnetic field in the galaxy. Everything goes around one way, but the Sagittarius arm is has a mind of its own and goes around the other way. The atomic hydrogen. This is the chimney I was talking about before, this big V-shaped hole. Look at all the filamentary structure in it. But look also at these faint ghosts, these dark shadows. That is cold atomic hydrogen seen absorbing the emission. He's getting closer. The emission from background atomic hydrogen. It's getting the very first stages of star formation. Mushroom clouds in atomic hydrogen, same physics. And the polarized interstellar medium. The total intensity sky and the polarized sky don't look the same. This thing is a 350 parsec stellar wind bubble in the Perseus arm that you just can't see in total power. So I think the boss says stop, so I think I'll stop there.
Questions? Anybody? Yes, Gerald.
Just an interesting thing to note, one of the big results from the Herschel Space Observatory was the prevalence of filamentary structure in the interstellar medium. which seemed to come as a big surprise, or at least was not suspected, but you saw it in yours, in the Galactic Plane Survey. Almost all filamentary structure.
Rob, you have a question?
Yeah, I have recollection of, we had a visit from Garth Westerhout in the early 70s when we were planning and starting to build the synthesis telescope, and he told us we would never have enough sensitivity to map H1 in any detail. I think we proved him wrong.
We proved a few people wrong.
My first AAS meeting, I was an undergraduate. I walked out of my hotel room, turned the corner, and the guy next to me, the room next to me, the door opened, and out walked in a bow tie with his cane, Garth Westerhout. And I saw his name tag. I said, Dr. Westerhout. And before I could say, it's so nice to meet you, he looked at my name tag and said, Tim Robichaud, how long has it been? All right. Okay, so let's thank Tom again.